All right, today we're diving into something that sounds, well, kind of out there, the geometry of imaginary numbers. And you're going to see how this idea, which seems totally abstract, actually unlocks this incredible hidden world of shapes, rotations, and beautiful patterns.
Okay, so this is the question that gets everybody, right? You see a number like 3 plus 4i and your brain just kind of goes, wait a second, that's like adding 3 apples and 4 oranges. It just doesn't work, you can't do it. So what is that plus sign even doing there? Well, here's the secret. It's not really about adding in the way we usually think about it. Not at all.
So to get what's really happening here, we have to do something kind of radical. We need to completely break free from the good old number line. We're going to stop thinking in one dimension and start seeing numbers in a whole new light, on a two-dimensional plane.
It all boils down to this one famous definition. I is just the number whose square is -1. Now, for centuries, mathematicians kind of treated this as a weird trick, a clever placeholder that didn't really mean anything in the real world. But it turns out they were looking at it all wrong. Its reality, its true power, isn't about its value. It's all about geometry.
And here it is, the big idea. I isn't just some number, it's a direction. Think about it. If our normal, real numbers live on a line that goes left and right, then imaginary numbers give us a whole new axis that goes up and down. That one little shift in how we see things, that's the key. That unlocks absolutely everything.
So back to that a plus b thing. That plus sign is really just a piece of notation. It's not telling you to add two things. It's giving you an address, like GPS coordinates. It's saying, hey, start at 0, go A steps horizontally, and then B steps vertically. See? It's not a single value on a line anymore. It's a point, or even better, a vector, on this awesome two-dimensional map we call the complex plane.
Okay, so now that we know complex numbers are just points on a map, what happens when we try to do math with them? Like, what does it mean to add or multiply these points? This, my friends, is where things get really, really cool. The old rules of arithmetic, they transform into these simple, visual, geometric actions.
Now, if you remember from algebra class, adding complex numbers is all about grouping the real parts together and the imaginary parts together. That's the rule. But what does that look like? Geometrically, it's nothing more than a shift, a simple translation. Adding a complex number is literally just sliding a point across the plane. If you've ever worked with vectors, this is going to feel very familiar.
Let's picture it. You've got two complex numbers, and you can think of each one as an arrow pointing from the origin to its spot on the plane. To add them, it's super simple. You just take the second arrow and stick it on the tip of the first one. Where you end up, that's your answer. Or another way to see it, the two arrows form a parallelogram, and the sum is just the long diagonal across it. It's a clean, simple, purely geometric move.
And hey, what about subtraction? It's basically the same deal. Subtracting a number is the same as adding its opposite, right? So geometrically, all you do is take the arrow you want to subtract, spin it around 180 degrees, and then add it just like before. That's it. It's all just about sliding points around this grid.
All right, so adding and subtracting are basically just sliding things around. That makes sense. It's pretty intuitive. But what about multiplication? Oh, this is where the real magic happens. This is where the complex plane just blows your mind.
So yeah, here's the big question. If you try to multiply two complex numbers using algebra, you can do it, but it gets kind of messy with all the terms. But what does it mean geometrically? It turns out it's not messy at all. It's something incredibly elegant.
Okay, let's start with an easy case. What if we multiply a complex number by just a regular, real number? Say we multiply it by 3. All that happens is you stretch its arrow, its vector, to be 3 times longer. The direction doesn't change one bit. It's still pointing the same way, just further out. That's it. We just call that scaling.
And now, for the big reveal, the real aha moment. What happens when we multiply by I? Watch this. The arrow, it swings exactly 90 degrees counterclockwise. The length doesn't change at all. It's a pure rotation. Let that sink in. Multiplying by I is a 90-degree turn. This is the proof. I isn't just a number, it's a command. It's the rotate by a quarter turn button.
So if multiplication is really all about rotating and stretching, then our usual x and y coordinates are actually kind of clumsy for describing it. We need a better language, and that language is called polar form. Instead of giving a street address, we're going to describe a point by two different things: its distance from the center We call that the modulus, and its angle from the horizontal axis. That's the argument. And here's why polar form is such a game changer. It makes multiplying complex numbers almost laughably simple. You want to multiply two of them? Just multiply their distances together, and then add their angles together. That's it. That's the whole thing. All that messy algebra we talked about, it just boils down to two simple actions: scale the length and add the rotation.
Now, this whole geometric way of looking at things, it's not just a cute party trick. It's unbelievably powerful. It lets us do some seriously complicated math with surprising ease, and it starts to reveal these beautiful hidden patterns baked right into the numbers themselves.
And this leads us straight to this super powerful shortcut called de Moivre's theorem. I mean, think about it. What does it mean to raise a number to a power? You're just multiplying it by itself again and again. So what does that mean geometrically? Well, you're just adding the same angle to itself over and over, and multiplying the distance by itself over and over. So to find a number to the power of, say, 10, you just raise its distance to the power of 10 and multiply its angle by 10. It takes what could be an absolute nightmare of algebra and turns it into one quick, simple calculation.
And now for the grand finale. We've been going forward, right? Taking powers, but what if we use the exact same logic and go backwards? What about finding roots? For example, what are all the cube roots of the number 1? Or what are the 5/5 roots of some complex number?
The answer is just beautiful. It turns out that the n roots of any complex number aren't just scattered randomly across the plane. No way. They are perfectly symmetrical. When you plot them, they form the corners of a perfect, regular polygon. You want the 3 cube roots of 1? They form a perfect equilateral triangle. The 8/8 roots of some number? They form a perfect octagon. It's this stunning, hidden symmetry buried in the very fabric of how numbers work. And this whole journey, this whole geometric perspective, it all comes together in what many people call the most beautiful equation in all of math, Euler's identity. Look at it. It connects the 5 most important constants in mathematics. And there's our hero, I, right in the middle of it. And now you can actually understand what it's saying geometrically. It's just a simple statement. If you start at 1 and rotate by pi radians, that's 180 degrees, you're going to land at -1. That's it. It's the ultimate proof of how this supposedly imaginary number creates a structure that is incredibly deep, incredibly real, and just beautiful.